For decades, hardware scaling followed a predictable ladder. Sequential logic in CPUs yielded to parallel rendering in GPUs, which yielded to purpose-built matrix math in neural processing units. NPUs are now standard infrastructure. AMD's Ryzen AI processors deliver 50 tera operations per second, while Qualcomm's Snapdragon pushes limits up to 220 tokens per second. This progression creates an expectation that a single, unified architecture will eventually succeed the NPU. That assumption is incorrect. Current NPUs inherit the bottlenecks of conventional digital electronics. They process data in static frames. They isolate memory from compute, and their silicon transistors face limits. Because no single successor architecture can solve all of these distinct physical constraints at once, the compute hierarchy can no longer climb linearly. It has to splinter. The primary force driving this architectural divergence is power consumption. Current projections show data centers consuming a tenth of the entire U.S. power grid by 2030. This chart maps out where hardware goes next. The timeline splits into 4 distinct parallel branches: neuromorphic, analog, photonic, and quantum computing. These processors are not competing for the same workloads. Each path represents an engineered solution designed to bypass one specific physical limitation of digital silicon. On the left, standard neural networks process static frames, drawing power constantly. On the right, spiking neural networks process asynchronous events, firing only when localized changes occur. Intel's Hollow Point uses this to reach 15 tera operations per watt, consuming 100 times less energy than GPUs. These systems are actively running complex AI tasks at the microwatt to milliwatt level in secure facilities, including the Hollow Point deployment at Sandia National Laboratories. IBM took a different approach to latency with its North Pole chip, placing all 192 megabytes of memory strictly on die. Eliminating off-chip data transfers entirely pushes inference latency under a single millisecond. Commercially, platforms like BrainChip's Akida run continuous autonomous in-vehicle sensing for manufacturers like Mercedes-Benz on extreme power budgets. The barrier to adoption is strictly software. Utilizing a spiking neural network requires developers to abandon standard frameworks like PyTorch and rebuild AI models from the ground up. Standard digital chips are constrained by the von Neumann bottleneck. Shuttling data back and forth between separate memory and compute units wastes roughly 90% of a digital processor's total energy. As shown in this crossbar array, analog AI processors store neural network weights inside physical memory elements. By passing voltage through these cells, they execute matrix vector math in a single physical step, bypassing thousands of digital clock cycles. Hardware from Encharge AI and Mythic proves the efficiency of this physics. In commercial configurations, these analog processing units deliver between 20 and 100 times greater performance per watt than competing digital graphics processors. The trade-off is precision drift. Analog signals naturally pick up noise and degrade. IBM recorded a 5% accuracy loss over 30 days due to conductance degradation. Because of this drift, these chips cannot be used to train AI models. But for edge inference, where energy efficiency dictates what devices can operate autonomously, the raw efficiency outweighs the minor loss in precision. Photonic computing uses photons instead of electrons to perform calculations, allowing execution at the speed of light with massive parallelism through wavelength multiplexing. In 2025, Lightmatter ran state-of-the-art neural networks entirely on a photonic processor. Combining 1 million photonic components with traditional transistors, the unit delivered 65.5 tera operations per second while drawing only 78 watts of electrical power. This chart reveals the immediate application for optical hardware. Over 3 years, AI model parameters grew by a factor of 240, while interconnect bandwidth only doubled. Optical interconnects like Lightmatter's Passage M1000 bypass this bottleneck, providing terabits per second of bandwidth to feed massive datasets to GPUs faster than copper wire allows. Full optical computing depends on hardware that does not yet exist. Because there is no viable optical memory, systems are forced into a constant, inefficient cycle of converting photons back into electrons to hold state. Quantum processing units exist completely outside the logic of the other branches. They do not run existing AI workloads more efficiently. They exploit superposition and entanglement to solve discrete optimization and simulation problems that are mathematically intractable for any classical system. Google's 105-qubit Willow chip recently solved a computation in under 5 minutes that would require 10 septillion years on a classical supercomputer, achieving the first verified below-threshold quantum error correction. Quantinuum's Helios processor set a critical benchmark by producing 48 error-corrected logical qubits from a base of 98 physical qubits. This near 2-to-1 ratio proves that fault-tolerant computing requires far fewer resources than previously estimated. As a result, industry roadmaps across IBM, Google, and Quantinuum now converge on practical, fault-tolerant quantum computing between 2029 and 2033. These machines will not be scaled down into personal devices. They will operate exclusively as highly specialized, cloud-accessible accelerators coupled to traditional processors. Extreme hardware specialization is already actively reshaping the data center. Groq's language processing unit strips out data caches entirely, utilizing a static RAM architecture to deliver language model inference at 300 tokens per second. Cerebras attacks latency by scaling up, printing 4 trillion transistors and 900,000 cores across an entire unified silicon wafer to output 125 petaflops from a single continuous unit. These branches lead to a single heterogeneous computing model. Moving forward, intelligent runtime systems will actively route operations, standard logic to CPUs, matrix multiplication to NPUs, edge sensing to neuromorphic processors, and intractable optimization to quantum units. The primary engineering challenge has shifted. Fabricating the silicon is a known science. The true bottleneck is writing the complex software required to seamlessly orchestrate tasks across an inherently fragmented ecosystem. Measured, conclusive tone. Neuromorphic and analog systems are deploying to the edge today. Photonic interconnects will wire data centers by the late 2020s, and quantum processing units will join supercomputing clusters early next decade. The industry is forced to manage this immense physical complexity because AI data centers threaten to exhaust national power grids. The evolution of computation did not climb smoothly to a single elegant successor. It splintered into a complex tree because relying on specialized physics is the only way to survive the energy demands of artificial intelligence.